Okay, off we go. Well, golly, I mean, how do I phrase it? The next thing to say in the notes. By the way, apologies again for missing 2 classes in a row due to illness. I really thought it was the best choice that I not expose y'all to illness, and I hope that the recordings and extended office hours were a satisfactory substitute. Maybe I'll also comment. If you feel like there were some things that you still didn't get out of that part of the material, come to current office hours. Right, we've got office hours right after class, and be very happy to talk to y'all, fill in some gaps, answer some questions, what have you. Okay, so back into it. Back to Chapter 4. Recall we skipped Chapter 4 previously, coming back now to it, starting with Section 4.1. There's a bunch of stuff in 4.1 that's review, single variable calculus. And so I hope that y'all are good with, in particular, Taylor polynomials. And I expect that you probably are. But anyway, make sure that you are. Quick reminder, this is the formula for a Taylor polynomial. And a pretty reasonable question to ask is, but why? Right? Who dreamed this up? Taylor. Okay, why did Taylor dream this up? Right? What was his motivation? So there's different ways to answer that question. And here's my favorite. This Taylor polynomial, is the unique polynomial of degree k that mimics the function. This is the best copycat, you might say. This looks at certain key features of the function f, and this formula here is the only degree k polynomial that has all of those features, the same features as f. So it's a copycat. It's trying to sort of rip off what f is doing. Now, specifically, what is it mimicking? Well, it's mimicking f in terms of value, in terms of derivative, and then et cetera, and in terms of higher derivatives all the way out to the kth derivative. So, you can imagine that simply by virtue of this polynomial having the same value as f at a, that, then near a, it's going to have a similar value, right? But by virtue of having the same derivative, it'll not only have the same value at a, but it'll also kind of track the sort of the rate of increase of f. And then by having the same second derivative, it'll sort of track the curvature, and as it mimics better and better, you get better and better approximations near the value a. Okay, all right. So that's all review. Here's the thing: you can do the same thing for multivariable functions, and there is something called a Taylor polynomial of degree k. For a multivariable function. And again, I can write down a formula in here. Now, we're only going to write down the Taylor polynomial of degree 2. Gets a little weird in terms of notation, and we're not going to have any need in this course for Taylor polynomials beyond k equals 2. So anyway, here's what the degree 2 Taylor polynomial looks like, and it's a bunch of formula, but where does it come from? It comes from the same motivation. We want a polynomial that mimics f, that has the same value, the same, I'm going to say derivative here, but of course there's a bunch of partial derivatives, right? So same partial derivatives, the same second partials, third partials, etc., and all of the same kth partials, of course, most of which are mixed. So lots of mimicking that has to be done. And this formula right here that I'm going to talk about in just a second is the unique polynomial of degree k that mimics f in these senses. In other words, it's the rip-off, it's the analog of single variable Taylor polynomials. Okay. All right. So a couple things to say about this formula, though. Here we go. Okay, so what have we got here? What is that? Well, that's just the value of the function. That's easy. You can see where that comes from. What's going on with this second term here? Well, let's see. This says we're going to look at all of the derivatives of f, and we're going to multiply by this difference vector. And this is kind of what you might call a linear approximation of the change in the function, analogous to that term right there, in the same sense that the derivative allows us to take input changes x minus a, scalars of course, and estimate how much the function changes. Well, likewise, the derivatives, well, in here I've written it as a matrix. Of course, it's a gradient vector, right? This is a real valued function. Did I write that down somewhere? I didn't write that down. Okay, so this is supposed to be a real valued multivariable function. So I've written it as a derivative matrix, but this is a gradient vector, and just the same, and multiplying by the input change x minus a vector in this case, as opposed to scalar out here. You get an estimate of how much the function is changing. So very analogous. Okay, so here's where it gets weird. The second derivative is a complicated story. So it turns out this is what the second order term looks like. And you will notice that doesn't look exactly like the second order term up here. Oh, well, I guess I didn't. Anyway, let k equals 2 in that term. So there is a matrix down here, this thing called H. And then there's a matrix vector product, and then there's a dot product, and there were certainly no dot products that we noticed in the single variable Taylor series. So what's going on there? Well, if you get right down to it, this is the real formula, and if you just apply this in a single variable setting, what is this matrix? All of the second partials of a function that only has one variable. Well, if there's only one variable, there's only one second derivative. And so this is just, in the single variable case, it's just a scalar single variable derivative. And this is a scalar, and so this is just scalar times scalar. It's just a number, and this is just a number, and this dot product is then just multiply. And you can see it actually turns into the right expression. It's x minus a quantity squared, and second derivative, and there's that 1/2. So this will simplify in the single variable case exactly as it's supposed to. Right? It's a little unexpected that it looks like that. But it has to, because in the multivariable setting, what you really see is that second order approximations of functions are more complicated in multivariable than they are in single variable. And this is just what the answer is. And again, why is this the answer? Well, because this is the unique polynomial that mimics the function in the sense of satisfying these very properties. It just is. This is what it works out to be. Right? So, in some sense, the single variable Taylor polynomial is maybe a little bit misleading. It's misleadingly simple. And what we're seeing here is the true ugliness of what reality is in higher dimensions. Okay. All right. So notice this matrix is made up of second derivatives. Notice how it's arranged. By the way, it's exactly what you would think it is. Good news, you don't have to worry like you do with Jacobian matrices. Did I transpose it or not? Right? Did I get these? Did I accidentally do this right here? Right? And get it the wrong way? Don't worry about it, because if you're talking about a nice function, which we're assuming here, then these are the same anyway. So this is a symmetric matrix, and you, in some sense, can't accidentally transpose it. Or I guess you can, but it doesn't matter. Okay. All right. Okay, how are we doing? Everybody with me? All right. So this, believe it or not, is all I really need to say about Section 4.1. So I'm going to leave it at that for Section 4.1, and we are going to come back to this. This is going to help us when we get to a certain point in multivariable optimization. Okay. All right. On to 4.2. Excuse me. Okay. So, again, a flashback to single variable calculus. For the same reasons, of course. I mean, recall that, very often I like to flash back to single variable calculus to kind of, so you can see how the multivariable version is mostly the same, but perhaps a little different, which of course it was on the same previous page, and we're about to find the same thing here, and of course many times further in the past. Okay. Here's a very, very short summary of optimization in single variable calculus. If you have some function to be optimized, you want to find, where is this function the biggest? What we do there is comes out of what I'm going to call a process of elimination. And I think this is a really important point. Some students do get out of single variable calculus not really quite digesting that we don't really find maxima in single variable calculus. What we do is we actively eliminate most of the options as being impossible. And then there's only a handful of points left that we haven't eliminated. Now, at that stage, having eliminated most of the possibilities, there's only a couple that we haven't eliminated. It remains that we still don't actually know what's going on at the points we haven't eliminated. All we know is we don't know how to eliminate them, right? And so at that point, we have to do other things to figure out, well, what is going on at that point, right? But underneath it all, fundamentally, is a process of elimination. We identify actively, not maxima. It's a mistake to think that we actively identify maxima. Okay, all right. So the strategy for that is if certain conditions hold, if you're at an interior point where the function is differentiable and if the derivative is not 0, well, then that is not a maximizer. Because after all, if these three conditions hold, the function is increasing at that point in one direction or another. So, easy example, take this point right here. Right, that point satisfies all three of these conditions. That point is in the interior. The function is, again, I don't want to get formulas involved here, but you could imagine at that point, the function looks differentiable. And the derivative is not 0. So I claim that as a result of that, this function is increasing. And in fact, you can, in the case of this picture, you can see it's increasing, at this point, at least momentarily, at that point, it's increasing as you move to the right. So I argue there is no way that this point could be the maximizer, or local or global or otherwise. This can't be in any sense a maximum. The function is still in the process of increasing. You think this is the maximum? Oh, well, take a step over 1 millimeter to the right. The function just got a little bigger. So this isn't the biggest. Right? I mean, it's a very simple, unsophisticated point, really, if you think about it. It's this very, very lowbrow kind of strategy that by which we eliminate this as a candidate. Everybody on board? Okay. All right. So this allows us to eliminate most of the points in the domain. So good news, we can instantly rule out most of let's see, all of those points, and then let's see here, all of those points, and all of these points, and then all of those points. Those points are not maximizers for sure because of this argument. So what remains, and we do have to confess, there's certain points I can't eliminate. There are certain points that are not in the interior. such as that point and that point. They're not in the interior, and the argument, I've got to be in the interior so I can argue, look, I can go either way I want, and the function's increasing one way or the other. If you're on the edge, no comment. Right? There are certain points where the function fails to be differentiable, such as this point. And there are certain points where the derivative is not non-zero. Double negative. AKA there's certain points where the derivative is 0. Right? So these are the points that remain. And now, again, in terms of what's really happening with the optimization here, we're actively eliminating the green points, and we have no idea yet until we pursue further what's going on at the other points. But that's not how we tend to do business, right? The way we do business in practice is to kind of turn that around. Whoa, there we go. Kind of turn that around and kind of ignore all of the green, right? And we tend to say, all right, these conditions here, if any one of these things happens, any one of these 3 things happens, notice those are the exact opposites of these. Right? So if you have a boundary point, okay, well then it's not in the interior. If it's not differentiable, well then the requirement that f be differentiable fails, etc. If any one of these 3 things happens, then we know we've got something like, well, one of these, and I can't eliminate it, so I don't know what to do. So we give it a name. We call them critical points. Right? And so again, in practice, day in and day out, what we tend to do then, I guess I'd better just erase all of the coloring stuff. We look at where certain things happen. We call them critical points, and we claim that we found something. Right? And again, I emphasize, it's really quite the opposite. These are the points where we don't know what's going on and where we draw no conclusions. Everybody with me? Okay. So, same deal in multivariable. Morally equivalent. Same deal. Oh, and let me zoom back in. So now, more complicated to draw the picture. Here I'm drawing a function of just 2 variables because, well, it's already hard enough of a picture to draw. But of course, you could have a function of any number of variables. So let's keep it to 2 just for the moment at least, for artistic purposes. But there are various different things that can happen, right? And again, we have an active process of elimination to identify with great confidence certain points that are definitely not maximizers. And specifically, if you have a point like this one here, where it's in the interior of your domain and the function's differentiable and the gradient is not equal to 0, well, golly, if the gradient's not equal to 0, that means that the gradient is a certain vector there, like that. What does the gradient do? The gradient points in the direction that the function is increasing. If you're in the interior, whatever direction the gradient points, you can move in that direction at least a little bit, and the function is increasing as you go in that direction. How could this possibly be a maximizer? The function is still increasing. So we eliminate that as a candidate. And again, just like in the single variable case, this eliminates most of the points in the domain, right? And what it doesn't eliminate are a handful of points that fail one or more of these conditions. So if you have a point that's not in the interior, like this point over here, I can't eliminate that as a possible maximum, at least not by this simple-minded rule here, right? Because it's not in the interior, and so I can't. What if the gradient points sort of in a direction I'm not allowed to go? We can't. This process here does not eliminate it. Okay. So again, just like in the single variable case, the failure of any of these conditions, right? In other words, maybe it's on the boundary. Maybe the function fails to be differentiable. Maybe the gradient is 0. Right? If any of those things happens, then I can't draw any conclusions about it not being a maximizer. Said differently, I have no idea what's actually happening there. Right? And so again, in order to make it sound a little bit more positive, a little bit more constructive, we're going to say, oh, no, I found a critical point. Right? That makes it sound like we did something. The reality is these are points where we don't know what's going on. Everybody with me? Okay. All right. And I guess I should look at this picture here for a second and talk about what we're looking at here. So there are different kinds of things that can happen at various points where I don't know what's going on. One possibility is, it might be that, maybe I'm actually at the highest point. The maximum value of the function, that's possible. It's also possible that I'm at a point where the function is, it's maybe not the highest one, but it's at least the highest anywhere nearby. This is a little mountaintop kind of a thing. This is not the top of Mount Everest, right? But it's the top of, it's the highest point within, a couple hundred yards. So it's a kind of a max. It's a local max, we call it. Okay. But there are some other weird possibilities, and this is something that you don't see in single variable calculus. At this point right here, we have a very strange thing going on. This is what we call a saddle point, because it's shaped like a saddle in the sense that it goes sort of up in left to right, goes up and on both sides. So it's kind of minimum-like in that direction, but it's also kind of maximum-like in the forward-back direction. It's so it's a kind of a max if you're looking in that max if you're looking in this direction, and kind of a min if you're looking in this direction. So that's weird, and there is no single variable version of this. Okay. All right. Oh, and here's another nasty little point that we're eventually going to have to deal with. If you ask, what about all of these points? These points are not in the interior, aka these are the points that are on the boundary. Notice how many of them there are. In single variable, the boundary was a pretty boring sort of like, don't forget to check your endpoints, you got to kind of throw in those endpoints, and there's only 2 of them, and so fine, it's 2 extra points to check, no big deal. Here in the multivariable case, we have an entire continuum, right? We have a whole curve, every point of which is a problem that we're going to have to deal with. So that's going to be a whole nother thing. That'll be tomorrow, not today. Okay, how are we doing? Is everybody with me? Okay. I did want to show you one other thing. This is largely for fun, but I think it's also worth saying. So this thing right here, the saddle point. By the way, the name. I hope the motivation is clear. If you've ever seen a horse saddle, right? It goes up in the front, so you have something to hang on to. It goes up in the back, so you won't fly off the back of the horse, right? But then, of course, it has to kind of slope down for your legs, one on either side. So this, again, is something you don't see in single variable optimization, but this is not the only thing that you don't see. And there's other sort of weird things that happen only when you get into higher dimensional cases, and I'm going to show you one called the monkey saddle. I just did a Google image search, and there's a bunch of pictures to choose from here, so maybe I'll just click on this one. And you can see it's kind of got little valleys for your leg there on the left and for your leg there on the right. But then what's going on with this third little valley here? Well, that's where the monkey's tail goes, which is just adorable, right? And they've even got a picture over here. Somebody drew an actual monkey sitting on top of there. And so, comfortable arrangement for his tail. What I think is even funnier is if you scroll down, and you have to go down pretty far, but this is just a Google search for monkey saddle, and turns out there are hits on that aren't math related, and some people have actually put a little saddle on a dog and put a little monkey on it. Anyway, so if you want to see that, it's scroll on down and you'll find it. Okay. Alrighty. How are we doing? Is everybody all right? Okay. So let's do one. Right, we're going to find the critical points. Now, I emphasize, as of yet, we don't know what to do once we've found critical points. Right, and we're not going to be able to draw any conclusions about these critical points just yet. But anyway, for the moment, let's find the critical points for this function right here. And we're going to go through this process here. We're going to check the three different versions of how you might find a critical point. You got to see is it a boundary point? So look for boundary points. Look for points where the function fails to be differentiable. Look for points where the gradient is equal to 0. We're going to do that here. This function's defined on the entire plane. Right? It doesn't fail to be defined anywhere. What's the boundary of the entire plane? There is no boundary. Right? Anywhere you are in the plane, you're in the interior. And so, well, there's just no critical points. And I'm going to call that good news. But we checked. There weren't any. Okay, next. Differentiability. Are there any points where this function fails to be differentiable? Yeah, it's a polynomial. It's differentiable everywhere. So again, bad news, we didn't find any, I suppose one could say. But good news, we checked. This function is good, differentiable everywhere. So I think of this, again, as being kind of good news more than bad news. Okay. Are we good so far, everybody? Okay. All right, and then we have to check the third condition, and that is, I need to know where is the gradient equal to 0. Well, I'm going to compute the gradient. There it is, to C. And now we check to see that gradient we computed, is it actually equal to the 0 vector anywhere? And, of course, notice for this to happen, this equaling 0 would require that x be plus or minus 1. And this, having to be 0, would require that y is equal to 0. Okay. And these statements here give us 2 critical points. There. Everybody happy? Yes?
Could you explain the first point again about define on R2 and every point on the
Yeah. So this condition here that we're looking for points that are on the boundary, right? The reason we have to look at points on the boundary is because if you're at the boundary, the mere fact of the gradient being non-zero doesn't allow you to eliminate that point as a possible possible maximizer, because if the gradient points this way, the argument of, then just go in that direction, and the function's increasing, well, you're not allowed to go in that direction. That would take you off of the set, right? So the point is, boundary points, you have no process of elimination. Every boundary point, you can't eliminate, and so I like to call them critical points. So we have to check and see if we have any boundary points. And in this case, if you're on R2, there just aren't any boundary points, right? No matter where you are in R2, you're never at the edge. Does that make sense?
Yeah.
So wherever you are in R2, whatever direction the gradient points, go that way. The function's increasing. Can't be a maximum, right? The argument sails through no problem. Is everybody happy with that? Yeah. Yes.
So if we have an upside down parabola,
Yep.
This method would give us a minimum, right? What do we do in that situation?
So keep in mind, all we're doing right now is finding critical points. We have yet to draw any. We have no methods yet for how to classify critical points and see what's actually happening. So yeah, for the moment, we who knows? And notice that I stopped right here. These are critical points. Probably something interesting is happening there, but I have no idea if, and I have no idea what. Yeah. Okay, so we'll get to that in a minute. All right, now the good thing about this example, the algebra was really easy, right? Going from there to there, nothing to it. Kind of the formula for x, just boom, easy. It practically fell in our laps. Okay, bad news. That doesn't happen very often. Here's sometimes you have to deal with uglier cases. Here's one. I'm going to skip the how did we get here part, but let's suppose that this is me setting a gradient equal to 0. Let's just say. So that being the case, this says that x squared's got to equal to y squared. That part's easy. Here's the problem. X squared equals y squared. There's really kind of two versions of what that might mean. And we don't know which it is. It could be that x is equal to y. But it doesn't have to be. It also, just as well, equally well, could be that x is equal to negative y. Right? And so this is bad for two reasons. On the one hand, it's bad because it's twice as much work. And I've got to go down track down each of these leads in some sense and see, well, where does this one lead? And then separately, where does this one lead? So it's twice as much work we're looking at. But also, the other thing is it's really easy to kind of accidentally forget. A lot of students will just say, x squared equals y squared, therefore x equals y. And that's just wrong. It's importantly wrong, and you're going to miss critical points that way. So heads up. Be careful about that kind of thing. You can't make assumptions about pluses and minuses. So let's follow through the cases. We'll start with x equals y. And here's the thing. If x is equal to y, and if we look at this equation right here, right, and you plug in x equals y, then what we get is, let me do it like this. We get that equation because x is equal to y, and therefore this x times y is just y squared. And we can solve for y, and we get these, which gives us 2 critical points. Right? And by the way, just to be clear, how did I get those points out of only knowing y? Well, if you know y, then you know x. Everybody with me? Okay. All right, but again, that was just case 1, right? Case 1 gives us these 2 critical points, but it's also just as valid, or just as likely, or just as relevant, if you want to say it, that maybe x is negative y. And if you plug that into this same equation here that we had before, right, then that turns into, different algebra. Right? Notice that these 2 things here are not the same. We get different algebra for y because we're making different assumptions about the relationship between x and y. So you got to see where that leads as well. And okay, so here we go. If we have this algebra, again, solve for y, you get these 2 possible values of y, and therefore these 2 critical points. Whoops, and then I wanted to, Okay, so 2 possible cases that come out of this equation. You got to check each of them, and they give us different critical points. Well, not at least, partially different critical points. Said differently, if you were to oops and forget that case, right, then you would absolutely, completely miss that critical point right there. Okay. Alrighty, so that's bad news. I'm sorry about that, but that's just the nature of the beast. Yeah. Okay, what do we do with critical points once we've found them? So we've got something called a second derivative test. And y'all remember the single variable second derivative test. I'm going to give you my point of view on, kind of how to think about it. And, you can think about it in terms of concavity, and that's nice. That's all fine. But, it's a better segue into the multivariable version if we think about the second derivative test a little bit differently. And that is in terms of Taylor series, or Taylor polynomials. Right? And so if you're at a critical point, that means the derivative is 0. Well, it could be an endpoint. It could be... Anyway, for the critical points for which the derivative is 0, this whole term goes away, right? And don't forget that this first term is just a constant. So, if you want to know how does the Taylor polynomial behave, and keep in mind the Taylor polynomial is mimicking the function, right? So by extension, if you want to know how the function is behaving locally, nearby this critical point, you can pretty much just look at the second order term. Right? This second order term pretty much tells the story. And, from here, it's, easy to reason. If the second derivative is positive, that means that this term is positive. That means that the function is bigger away from the critical point, and that means that you have a minimum. Right? And likewise, if it's negative, then this is negative. That means the function is less away from the critical point. That means you have a maximum. So that's an easy way to algebraically motivate the second derivative test. And pretty much the same thing happens with multivariable. So here we go. So again, we're assuming we're at a critical point, namely one of the critical points where the gradient is 0. That means that this term goes away. Again, this term is just a constant. And so the behavior of the multivariable function is mostly controlled by what's happening with this term. Everybody with me so far? Okay, so now y'all have all had Math 218, and y'all learned a lot of linear algebra ideas in Math 218. Some of them come up here, and I'm not going to focus on that part of it because time is tight. And but anyway, hopefully you may recognize at least what this expression is an example of. It's an example of something called the quadratic form. Everybody remember quadratic forms from Math 218? Okay, well if you don't remember, then it'd be a good thing to go back and remind yourself. And quadratic forms sometimes have the feature, depending on what this matrix is. Sometimes they might be something called positive definite. Sometimes they might be something called negative definite. Sometimes they might be something called indefinite, right? And there's also this semi-definite stuff that we don't want to talk about. Same story though. So if this matrix here is positive definite, that means that this expression is always positive away from the critical point. And if that expression defining the behavior of the if it's always positive, that means that the function is increasing away from the critical point, and that means that you have a minimum. Everybody with me? Notice how it's totally analogous to the single variable version. Right? And then likewise for negative definite and likewise for indefinite. Okay. All right. So what it comes down to then is how to decide when your Hessian matrix, when is it positive definite, negative definite, or indefinite so that you can draw your conclusions. And here's where I am going to sweep a lot of linear algebra under the rug. I've hit some highlights down here, and if you're interested, you can use the fact that the Hessian is symmetric to conclude that it's diagonalizable. I hope that rings some bells. If it's diagonalizable, then you can draw conclusions about its eigenvalues and blah blah. You can do a change of variables and rewrite the form of the quadratic form, and then you can draw certain nice conclusions based on the fact that this looks nice and simple. Now, I just gave you about a 20-minute discussion of linear algebra in 20 seconds. So anyway, but this hits some highlights, and if you want to try to piece together the details, it's a nice discussion. But you don't have to. It's not required for this course. Here's the punchline, right? How we actually make use of these observations here is if this is called the second derivative test. By the way, this is only for 2 dimensions. The book writes down the general case when you're in more than 2 dimensions, where you have more than 2 variables for your function, and we're not gonna deal with that in this class. And it should be so noted on the content syllabus. It just gets more. It turns into an awful lot of trouble, basically. But in the 2-dimensional case, it's just not that bad. And here's how it works. If your Hessian determinant is positive, then you get a familiar result. And that is, you just look at the second derivative. In fact, it doesn't even matter which unmixed second derivative you look at. I like to look at fxx, but you can use fyy if you want. Cannot be a mixed. It's got to be one of the diagonal second derivatives. Positive means min, negative means max. Just like in single variable calculus. Very familiar. So that's great news. Right? I emphasize, though, this is only if the Hessian determinant is positive. That's a big deal. There's other possibilities. The Hessian determinant might be negative, and this is the sort of an unexpected weird one. If the Hessian determinant's negative, that's actually a saddle point, and it's very counterintuitive. It's tempting to think, well, shouldn't I be looking, though, at the second partials in both directions, and don't I need... It turns out you don't. And again, there's some sophisticated linear algebra that goes into that. But the Hessian determinant's negative, saddle point. Guaranteed. Okay. And if you get 0, then the test fails, and you can't draw any conclusions at all. And this is another important thing to realize. I mean, if that Hessian determinant is 0, some students might look and figure that, okay, well, yeah, but I can still see the fxx, and I can still see the fyy, and surely I should be able to draw some conclusion from that. It turns out, no, you really can't. It's more complicated than it looks, and you really can't draw any conclusions at all. Okay. All right, so in action, previously we looked at this function. Oh, yeah, question?
Are fxx and ffy always going to have the same sign?
No. I'm sorry, one more time.
fxx and fyy, because you said it doesn't matter if you pick fxx?
Yeah, so in this case, they have to have the same sign. Okay. Because, real quick, we know that our Hessian matrix is symmetric. So I know that the non-diagonal entries are the same. And so the determinant of this is AB minus C squared. And if this is positive, then this has got to be positive. Okay. You see what I'm saying? And so, as it happens, positive determinant means that those diagonal entries are either both negative or both positive. Yeah, a little weirdo thing, but yeah.
Do you ever have a case where your Hessian determinant is greater than 0, but then your second derivatives are 0?
Yeah, and that's another case where the test fails. Yeah. So the test only works specifically in these two cases, and the inequalities are strict. Yeah, absolutely. Okay. All right, so again, in action. Previously, we studied that function. We found these critical points, and we threw up our hands like, okay, well, all I know about these points is that I can't eliminate them. And I don't have the slightest idea what's actually happening at these points. So let's see what we can do about that. And we're just going to play the game up here with the second derivative test. And I'm going to need the Hessian matrix, clearly. And so we compute the second partials, make a matrix out of it. There you go. Easy to take the determinant. There it is. Right? And now it's just kind of a matter of plugging and chugging. And so we'll start with this point, this A, -1, 0. And okay, step 1. Let's see, what is the Hessian? The Hessian determinant turns out to be -12. Negative means saddle. How we doing? Okay. All right. Now let's look at the other point. Let's see here. Looking at 1, 0 now, and again, I've got to plug into the Hessian determinant, see what happens, and plugging this in, I get positive. Positive means now I've got to next look at I shouldn't do that like that. I need to look at the fxx, the top left entry, in other words, of that Hessian matrix, and see, is that positive or negative? And well, okay, so let's do that. Let's take this point, plug it into there specifically, and what we find is that it is 6, which is positive, and that means local min. Everybody see how I use the... And again, notice all I'm doing is I'm just plugging numbers straight into this test and following the instructions, and out come our answers. And, yes, sometimes the test will fail, but this is very useful most of the time. All right. Okay, so let's see here. Oh, we are short on time. So you found some critical points. So you've classified your critical points as local maxes, local mins, what have you. Suppose you have a local max. Maybe you have 3 local maxes. Does that mean that you have a global max? And the nasty reality is that no. It doesn't. And furthermore, it didn't in single variable calculus either. Right? So a couple of examples to remember, and I hope you remember this kind of stuff from single variable. If you have a function that's defined on an interval that's open on one end, right? Well, your function could do this move where it asymptotically approaches infinity as you approach that open endpoint. And some people will say, well, yeah, but you're not allowed to, the function's not allowed to equal infinity, real valued function and all that, and infinity is not a real number and all that. Well, I'm not defining the value of the function to be infinity anywhere because I don't have to, because that endpoint is not part of my domain. So, yeah, we've got a local maximum here, but that's not even close to the maximum value of the function. In fact, this function has no maximum at all. No absolute maximum at all. So likewise, other things. If your interval is open-ended in one direction, well, the function could just steadily rise like that. There is no maximum. If the function didn't have to be continuous, if you had a discontinuity, like let's say right there, well, the function doesn't have to have a maximum. This function gets arbitrarily large. Right? So there's all sorts of things that can go wrong in the question of, do I have a absolute maximum at all? It turns out these are the only three things that can go wrong, pretty much, right? Right? Whoops. The function might fail to be closed. Excuse me, the domain might fail to be closed. The domain might fail to be bounded. And the function might fail to be continuous. But if none of those things fail, if you have a domain that is both closed and bounded, we like to use the word compact, by the way, for a set that's both closed and bounded. So if you have a compact domain and a continuous function, that function will achieve a maximum value somewhere in that domain. All right, I am out of time at this point, so I'm going to have to draw the line right there. And we will pick up here on Wednesday. And see you later. Good to see you all again. I hope everybody's staying well.